Embeddings is nowadays a key concept and a huge subject in the space of neural language processing. Embeddings have a fascinating history and brought surprising results. They had and they are still having unexpected, unpredicted, amazing developments. And the way we will cover them, it's going to be a very basic coverage. We will introduce the main concepts, and if later on you want to go deeper, we really encourage you in doing that because we think that it's really worthwhile and it's really fascinating and rewarding subject. Working at our encoder-decoder model based on RNN, we are faced with the problem of encoding text in a suitable way so that our numerical algorithm can understand, can process. So we can be able to input words in our RNN and then receive words as output. And since our model is able to handle only numerical data, we must be able to transform text into numbers, and when we get the output as numbers, we must be able to transform those numbers back to text. So how can we do this? And the first idea that comes to mind is what is shown in this slide. We could list off the words that we have in our vocabulary, and we can just associate a specific number, for example, an integer number, to each of the words. So, for example, the sentence "the cat is black," we could search for the word "the" and see that it is linked to the number 8676. And we can just provide this number to our network, and for the second word we have cat, and so we will provide 3203 and so on, and also the other way around when we receive the output. The problem with this approach is that our network operates in the continuum space. So if we think about how the input numbers are handled in the single neuron that we saw and the operation that the network performs, we must expect that if we input two numbers that are very close, the model somehow expects that those inputs are quite similar. And for text, it means that the network assumes that the usage that you can do of that word, the implications that the word have, the meaning, in other words, is similar. And of course, if we build a vocabulary and we associate it with the integer numbers in this way, we see that there is really no association between the similarity of the numbers and the similarity of meaning, because we have is and island that are close. We have candid, which is 3202, and a similar word could be white, and white is going to be around the bottom of the list. So this kind of input, this way of representing words is going to be very confusing for our model, because it will inevitably assume false meanings within our inputs. So this approach is not usable, and we have to find something better. A second approach that we can follow, much better than the first, to encode text as numbers, is to use one-hot encoding. And one-hot encoding is based on the concept that we have vectors that are composed of all zeros except one spot, which is 1. So if we have, for example, this sentence, the cat sat on the mat, we can distinguish the words in a way that the network see that the spot, the place in the vector corresponding to one of the words is marked as 1, and the other places are marked as zeros. So when we will input this vector to the net, we will provide 0 everywhere, except we'll provide a 1 that will tell the model which word we are considering. And what is nice of this approach is that all the words are the same, and the distance between them is always the same, because the distance is always 2, because there are always 2 places that are different from any other vector. So, for example, we can have, if we want to represent all our vocabulary, we must arrange a place for each of the words. So our vectors are going to be as long as our vocabulary size. And this is one of the drawbacks of this approach, because the vocabulary size can be in the order of the tens of thousands, but for most serious models can be also in the range of hundreds of thousands. So if we want to input a word in a vocabulary that can become huge, as 500 and 500,000, we have, for each word, we have to input a vector which size is 500,000 places, and all of these places will be zeros except 1. And these have some negative implication also on the processing, because we must remember that if we have some neuron here on the first layer that we will process this vector, each of these nodes will have 500,000 connections. So here we will have for each of them 500,000 weights and so on, and the computation is going to be, let's say, not trivial. Another drawback is that we said that all the words are coded with the same distance, and there are no particular relationships between words, which is somehow a positive thing, but we also we avoid false relationships of meaning in the input, but we don't even have positive or good relations with the meaning, because all the words have the same distance between them. So, for example, if we say candid or white, they have the same distance that we can have between white and black, or between black and airplane or potato or any word, which is a limitation that we can try to overcome with the next approach that is proposed, which is embeddings. Embeddings are, in a way, a case where we apply the principle that we introduced when we initially discussed about neural network. If we have a complex problem and we don't know how to solve it, or we don't want to solve it, and one thing we can do is that we can design a neural network model with some parameters and some weights to be learned in training, and just let the model learn and solve that problem for us. So in embedding, what we do is that we take those huge vectors that we were discussing in the previous slide, where we represent each word as a one-hot encoded structure, where we have all zeros and just one. And we give this input to a machine learning model, which we train on a very simple task that can be, we assume a generic task, and we don't spend the time in dealing with this task. But whatever the task, we build this model with the first network layer that transform this huge vector in a much smaller vector. Let's say we go from 10,000 to 300 as a size, and in between, as we saw a few times already, we have a matrix here of weights. So what we do is that we have a matrix of weights that we can learn. Initially, they have random values, and during the train, they get proper values. So we trained this model on a task which is based on input that are words, and that has some output that is any classification of the text or some other target that we want to achieve. If we do this, and it takes some leap of faith, but it's true, and it's been seen and demonstrated by many works and papers, and you can find references all over the literature. What we see is that the model learns the matrix U weights in a way that each of the input word is transformed in a much shorter vector that we call embedding vector. That is a specific vector for each word, because if we look at our usual formula where we have a vector by a matrix of weights equal a vector in the next layer. We saw this already many times. So this is layer 1 and this is layer 2. So what happens is that since the vectors that we provide here is made of all zeros and just one, this multiplication, what it does is just selects one of the rows of this matrix and brings it here. This is because this guy is multiplied by 0, this guy by 0, this guy by 0, then here we have 1, and this guy by 0, and so we have 1 here. And the same for the other columns. So we can say that somehow the matrix of weight has for each row the embedding representation of one of the words. So here we have the fourth word that we are asking for, and so we get second, third, we get the fourth row in the matrix, and this is passed along to the rest of the model. The main finding in all these, and the key property to consider, is that when we train this model, whatever the simple task is in predicting some output, what we see is that this matrix of weights is learned, and this matrix, as we said, contains the embedding representation for all the words. And what we see is that if we look at these vectors, and especially if we draw these vectors as point in a graphical representation, which in theory should be of, for example, 300 dimensions, because a vector of length 300 is equivalent to a point in a space of 300 dimensions. Of course, when the dimensions are 3 or more than 3 are impossible to visualize, but there are mathematical techniques that are able to squeeze the number of dimensions and give us a good graphical representation, even in 2 dimensions. So if we squeeze these vectors in 2 dimensions, we see that these vectors that any model learns, if built with this architecture, these vectors have really amazing properties. And there is a very interesting and rich literature on this subject. The main property that we will take into account and that we will consider here, because it is already enough interesting, enough useful for us, is that words with similar meanings have similar embedding vectors, which means that words with similar meanings are represented by point in this graphical representation of the vectors, which are very close, which means that the numbers that makes these vectors are place by place, they are close to one another. And this is not surprising if we think that whatever the task that we are learning, the model learns the representation which is most useful to solve the task. And the most useful representation for the rest of the model, which will contain other, presumably other network layers, is that if we have words with similar meanings, those words must have similar representation so that the model can give similar results and treat them in a similar way. So, for example, the model learns a representation which is useful if it learns to represent hotel and motel with two vectors that are much more similar than, I don't know, motel and airplane. So this is what embeddings are, and this is the representation which is widely adopted. And if we look at that, we see that if we have a model and we provide the one-hot encoding, and then we have this first layer, and we produce the embeddings, we really haven't gone around the issue of dealing with huge vectors and have very complex computation, because each of these neuron here will be considering the input of many inputs on the previous layer. So this is something that it's still done in many occasions, and we will see it in the rest of the presentation in the model that we will be building. So one approach is that in a model we train the embedding matrix layer as a first layer of our model, and we train everything together. A second and most interesting approach that here is actually written as the first is that we can find on the market, we can find as open source nowadays many embeddings matrix and many embedding weights set for all kind of language vocabularies that are already trained, and we can use them off the shelf. They are trained on Wikipedia articles or other large corpuses, and or better, large corpora, and we can just download them and use them, and that prevents us for having all these first part in our model. We can just, for each word, get the proper embedding, which is much shorter, and it's also much more helpful since it embeds a meaning of the word, and we can just use it and feed these embedding encoded input to our model. If we now look back at our encoder-decoder architecture, we have here the encoder part. We now understand better the way it is designed, because we know that there is an encoder RNN, which is drawn many times because we consider several time steps, but it's always the same RNN and the weights are the same. We know that in the encoder we are going to encode a sentence, so we give the input of some words and the question mark, and we know that we are using an embedding layer that transforms this input text in a numerical representation. And in the model that we consider, we are training the embedding layer. We will have here a matrix of weights U, which is trained together with the rest of the model, with all the weights and parameters that we have in the model. So essentially we have weights within the RNN. So we have our hidden state, which is passed along from one step to another, and the last of the hidden state become the encoding of the phrase, because it is the vector, which is the last state of the encoder, but it's also the first state of the decoder, because it will be given as input to the second half of our model. And the second half of our model is quite similar. We just have a different RNN, because this is the decoder RNN. And here we are not only providing an input, but we are also getting an output for each step. And the output that we are getting is, you can see it as if we pass it through a layer, which is the opposite of the embedding layer, so that if we have a transformation here that maps a word as a one-hot to the same word as embedding, we have a transformation here which is the inverse, because we have an output which is in the form of an embedding, and we transform this output in something that we want to be similar to a one-hot, even if since this embedding is not be a perfect word embedding, but it's going to be a prediction. We will get some vectors that will not have all zeros and one, but they will have probably many 0 or close to 0, and some 1 or more spots that have a high value. So the basic idea, to stay very simple, we can take the highest value and decode that one-hot vector, getting the value that is the top value in all the vector, and we can say, okay, the word we have is I, for example. And what we do is that, for example, if we are at prediction time, so we don't know the right answer, we're just asking the model for it. The model says I, okay, so to help the model, we give I as an input to the second step, and we ask for the prediction, and this is a question answering system, and the answer will be M, and so we give M as input. Of course, this is transformed in embedding, and we get fine, and then we get end of sentence, and this is the end of the sequence that is generated. So at prediction time, we just take the output word that we get and we provide it to the next step in the model. When we are training the network, what we do to help the training is that whatever word is predicted, even if it is wrong, we just provide the right prediction of the previous step to the network so to speak, keep it on the right track. So even if the network here predict was, we say, okay, the right word is M. So since we are training it, we say, okay, assume the output is M and tell me the next word. And so with the coverage of embedding, we are able to see what is happening also in this layer. Transformation of the word has one-hot to embedding, and inverse transformation here to a vector, which is in the form of one-hot, and we can, to make it simple, we can assume that we take the highest value in this vector and we take it as the input value that is generated by the network. Having described the basic landscape of the technology before attention came around, we will now introduce some of the limitations of the models based on encoder, decoder, and RNNs, some of the pitfalls that justified the future evolutions and motivated the introduction of the concept of attention. We see here on the upper side an example of a very small encoder-decoder toy model that is mapping a sentence in German that I don't even dare to pronounce to an English translation, which is please come here. And if we think about this model, we see that all the encoding phase is finalized in producing one single vector that in the picture is called C as context. And this intermediate vector contains all the meaning that will be available to the decoder to produce the translation. What was observed in the result? The results is that the performance of these kind of models were decreasing with the length of the sentences that we deal with. What basically happened is that when we looked at the encoder network, it is quite natural that if we think that an input sentence can be easily of 30 or 50 words, when we get to the end, the first part, the beginning of the sentence, has been processed many steps ago. So to speak, the network has forgotten in a way the first part. And there were many developments and papers and ideas that try to overcome this issue and this limitation. And one of those was to just feed the sequence that we want to encode to the network backward. So since we can assume that the first part of a sentence is the one that rules the sentence and dictates what's going on and how the sentence is going. And anyway, from an empirical point of view, it was shown that if we just give the sentence backward, the results were a little bit better. And about results and how to measure them, we will say something later on. Another idea was to say, okay, but if we can give this the sentence backward, what we can also do is we can do both. So why don't we have a bidirectional encoder? So a bidirectional encoder is an encoder that is actually made of two encoders, and one is digesting the sentence in one way, and the other one is digesting the sentence, reading the sequence in the opposite order. So what we can do is that, okay, when we reach this final state here, and we reach the final state here, we can stack these two final states together, and we can feed this double vector to the decoder. And this also improved the results. Another large areas of improvements was trying to work on the RNN themselves. So there were evolutions in the RNN models that brought some more complexity in the model and in the capability. So to make RNN better are keeping state and keeping information for a longer number of steps. And this is what what gave birth to these models that we call LSTM, as long short-term memory units, and GRU as gated recurrent units. We now give a look to how the RNN model was enhanced to make it better at handling long-term state, and to deal with longer sequences of symbols. And these evolutions are called LSTM and GRU. And of the two, we will be focusing on the GRU because They are the simpler ones, and they are enough to explain the kind of improvements that were made, and they are also the ones that are adopted in the attention-based model that is the final destination of our discussion. So if we look here on the right, we have just a refresher of the RNN that we already talked about. And in particular here we see how the RNN is able to compute the next state. And the model of the RNN is very simple, because the next state is computed from two inputs. And we have seen that each of those inputs is multiplied by a matrix of weights. And so here we can see like one of the input is projected by the weights on another layer. And here again, xt is projected by weights on another layer. And these two layers are just added up. And then, after adding them up, they are just passed through a nonlinear function. And the result is the new state. The evolution that was built for GRU on the bottom right, we see that the model is a little bit more complex, because we have this X input here that is used together with the previous state, which here is called I minus 1, where I is the current step, so I minus 1 is the previous step. And from the previous state and the input, we compute a new state for the current step, which is I. But this state has a hat, because it's just a candidate new state. So this candidate new state is going to be used to produce the actual new state, but this candidate is somehow competing with the previous state. So the previous state is also provided as a second candidate to be the new state. So the ability here is not also to calculate a new state and adopting it, but also to just make the previous state be the new state. This gives the GRU the capability to maybe go for 1, 2, or more steps without updating the state, because the network judges that it's not useful to update the state, and this gives the ability, when the network decides, to keep the state for a longer time. And how much the state is updated or kept from the previous step is decided by a parameter, which is Z. So here we have the mathematical expression which says if Z, we multiply Z to the candidate state, and we multiply 1 minus Z to the previous. So if Z is 0, we forget the candidate, we just keep the previous. And if Z is 1, is the other way around. Anyway, Z, which is called the update gate, is this extra gate that decided if we want to update the state or not. And how do we decide it? Of course, as usual, we have two elements. We have the previous state and the input, and we project them with the usual two matrices of weights, and then we sum them. And then we pass through a nonlinearity, which is the sigmoid. So the usual way, we create a gate, and the way the gate is, the position of the gate is decided by the model itself and is learned in two matrices of weights. We also have another gate, which is deciding when we create the candidate state. Besides using the input that we definitely use, so when we decide the new candidate state, we always use the input, but how much do we use the previous state? This is decided by another gate, R, and if R is 0, then we multiply 0 by the previous state, so these terms disappear. So the network decides to calculate the new candidate state just on the input and not on the previous state. So these add mode flexibility, and this gate is also learned by two specific metrics of weights that we multiply by the input and by the previous state, and then the result is added up and is passed through a nonlinearity, which is a sigmoid. We have described the kind of models that were popular before attention came around. They were based on recurrent networks, maybe enhanced as GRU or LSTM. They were using encoder-decoder architectures. We have seen the main limitations they had, so now is the time that we finally start talking about attention.